You hand an AI your tangled, broken code base. You stare at the blinking cursor in silence. Beat. Trusting a machine with that mess it is terrifying.
It really is like a leap of faith.
Yeah. You're wondering if it will actually fix the architecture or if it's just going to hallucinate a completely new disaster. It is a genuine moment of developer anxiety.
Absolutely. I mean, we are essentially handing over the keys to our digital infrastructure. You are asking a statistical model to understand human intent.
Right. And today on the deep dive, we are looking at the 3 models currently asking us to take that leap. Because we are in mid-2026 now, and the AI coding debate has essentially narrowed down to 3 titans taking up all the oxygen. We've got GLM-5.2, Claude Opus 4.8, and GPT-5.5.
Those 3 are absolutely dominating the conversation right now. Every engineering team is having heated arguments about which one is actually the most capable.
Okay, let's unpack this. We are going to look at what the rigid benchmarks actually say. We will uncover the real financial cost hiding behind supposedly cheap tokens. And most importantly, we're going to look at the results of 2 brutal real-world tests.
The side-by-side ones.
Exactly. A complex, interactive game build and a massive, frustrating bug hunt.
We really have to look past the marketing hype and the pristine release notes. We need to understand how these models behave when things get messy.
Exactly. But, the hype cycle always starts with the headline numbers. People love a clean, simple metric.
Oh, they do?
We see a high score on paper, and it looks incredibly convincing. It makes a complex neural network feel quantifiable.
It is human nature. We want a leaderboard.
Yeah.
But a high score on a standardized test does not guarantee real-world success. The mechanisms behind those tests are, well, they're often flawed.
Right, which brings us to the DeepSWE benchmark.
Yes.
DeepSWE is a test mirroring actual bugs in real code bases without internet access. It is designed to be rigorous.
The isolation is the key factor there. The model runs inside a restricted container. It has to ingest the issue, locate the faulty file, and write the patch completely on its own. No human developer can guide it.
The official stats for that test are pretty striking. GLM 5.2 scored 46.2% on DeepSWE.
Wow.
Yeah. That is currently the top result for any open-weight model.
It is an impressive milestone for the open source community, but the landscape gets more complicated with long horizon tasks.
You mean tasks requiring sustained logic over multiple steps?
Exactly.
That is where the FrontierSWE benchmark comes in. On those long horizon tasks, GLM hit 74.4%.
Okay.
That puts it just behind Claude Opus 4.8, which hit 75.1%. And surprisingly, GLM actually edged out GPT-5.5, which sat at 72.6%.
On paper, those margins are incredibly thin.
Yeah.
If you are looking at a statistical tie, it implies the open model has completely caught up.
But I look at those numbers and I think about my own projects. If the open model is supposedly tied with GPT, why does it lose the plot with my code?
Yeah.
Why do models that ace these tests suddenly fail on messy projects?
Because benchmarks are fundamentally controlled environments. They're tidy, sanitized sample problems. The AI knows exactly what the grading script wants, but real-world coding requires adapting to undocumented, unpredictable chaos.
It is like watching a national spelling bee. These kids memorize thousands of incredibly complex root words.
Right.
It is highly impressive under pressure. But spelling the word chrysanthemum perfectly does not mean you can write a compelling novel.
Right, and a novel requires handling messy, unpredictable human elements. Real software projects are exactly like that.
Yeah, they are.
You have vague feature requests from product managers. You have strange legacy code written by a developer who quit 3 years ago.
Oh, the worst.
And you have comments that actively contradict what the function actually does.
A benchmark never tests for human unpredictability.
It can't. The AI simply cannot handle the ambiguity. It was trained to find the mathematically optimal path, not the context-dependent path.
So real life has no script to follow. Since benchmark scores are largely an illusion, the next thing everyone looks at is the price. If they all score roughly the same on paper, we just want the cheapest option.
Sure.
But the sticker price hides massive practical hurdles.
The pricing structures of these APIs are notoriously difficult to map to real-world budgets. You have to scrutinize the input costs versus the output costs.
The token pricing per million is wild right now. GLM is $1.40 for input and $4.40 for output. Claude Opus jumps up to $5 for input and $25 for output. And GPT 5.5 is $5 for input with a massive $30 for output.
The gap there is staggering. GLM is roughly 3.5 times cheaper on the input side.
Yeah.
And it is 6 to 7 times cheaper when generating output.
Mathematically, it feels like a no-brainer, but I know from painful experience it is not that simple.
It rarely is.
I still wrestle with prompt drift myself.
Yeah.
I will start with a very clear, specific instruction to save money on a cheaper API. But 10 prompts later, the AI has completely forgotten the core architecture. It is just writing broken spaghetti code.
This is a classic example of the cheap token trap. A cheaper model often has a weaker attention mechanism over long contexts. It makes subtle logical mistakes. You have to constantly correct it.
And every time you correct it, you are resending the entire context window.
Precisely. If a cheap model needs 10 times the tokens to actually finish a job correctly, those massive savings evaporate.
You burn through your budget just trying to steer the model back on track.
Exactly.
Which brings up a really confusing aspect of this entire landscape. GLM-5.2 is an open-weight model. It has an MIT license.
Right.
If it's free to download, why are we still paying for it?
Because open does not mean lightweight. We're talking about a model with hundreds of billions of parameters. Those parameters are essentially the complex mathematical weights that make up the neural pathways.
You physically cannot load that into the local memory of a standard machine.
Not even close. To run a model of that scale at an acceptable speed, you need a massive, dedicated GPU cluster.
Wow.
We are talking about data center level hardware. So most independent developers still have to use an API service like OpenRouter to access it.
You are paying for the massive infrastructure, not the intellectual property.
Exactly. The licensing is free, but the electricity, the cooling systems, and the silicon certainly are not.
Open means accessible data, not free hardware. Beat.
That is the hard truth of where the technology is right now.
Just 'cause you can't run these titans locally and you can't trust the benchmarks or the raw sticker price, you are left in the dark.
Yeah, you really are.
The only truth lies in high-effort, side-by-side server testing.
You have to strip away the marketing material completely. The only way to know how they behave is a head-to-head matchup.
Right. Here's how you set up a rigorous real-world test. You give all three models the exact same prompt. You ask them to generate a step-by-step plan first, before writing any code. And you force them into their absolute highest effort modes.
That means utilizing codecs for GPT. You use OpenCode via OpenRouter for GLM. And you use Claude Code for Opus 4.8.
You are forcing the models to dedicate maximum compute to the problem.
Exactly.
But we need to clarify a huge misconception about how that compute actually works. A lot of people buy highly expensive laptops thinking it will make their AI coding assistants faster.
It is a very common misunderstanding of the client-server architecture. Your high-end laptop's RAM does not speed up the model's analytical thinking whatsoever.
Right.
Your machine is basically just a dumb terminal requesting data.
The heavy lifting is happening hundreds of miles away on the provider server. Your local machine only matters for the local preview rendering.
Right. If you ask the AI to build a WebGL demo or a complex 3D game, your laptop needs the power to render those pixels smoothly.
Makes sense.
If your local GPU is weak, the preview will lag. But the AI itself isn't slowing down.
And when you use these high-effort modes, you are going to wait. One public test showed GPT Pro responding in about 10 minutes.
10 minutes for a single architectural response is a lifetime in traditional development.
It is. But another test took close to 60 minutes for a full complex game build.
Yeah.
Whoa.
Oh.
2-sec silence. Imagine it processing hundreds of billions of parameters just to find one missing semicolon.
The scale of computation is genuinely breathtaking. We are routinely spinning up supercomputers to do the digital equivalent of proofreading.
So buying a faster laptop won't make the AI code any faster.
No. The server processes the logic. Your laptop just renders the resulting pixels on the screen.
Servers do the thinking. Your laptop just displays the result.
Precisely.
Oh, okay. So we take all that massive server power we just talked about and we apply it to creation.
Right. Generating a function is one thing, but turning a single text prompt into a fully interactive game is something else entirely.
It is the ultimate test of synthesis. You are asking the model to build an interactive experience from nothing but language. Let's break down Connor Dart's public test on X. He gave the models one single prompt and asked them to build a working marble puzzle game.
Video games are a phenomenal stress test for AI.
Because they require multiple, heavily interconnected systems running at the exact same time. You need a physics engine, you need visual rendering. you need user input controls, and you need core win-state logic. It all has to happen simultaneously at 60 frames per second without crashing.
It forces the model to juggle parallel logic tracks.
Yeah.
If the physics update loop conflicts with the rendering loop, the whole thing falls apart.
The results of this game build were incredibly telling. GPT structured the code beautifully, is mathematically sound and highly organized.
Yeah.
But the game itself lacked a playable feel.
It was technically correct, but experientially rigid.
Right. Now, GLM was honestly impressive for an open model. It managed to build a functioning game.
Okay.
But those token costs we warned about really piled up. It required a massive amount of trial and error and reprompting to get the physics right.
Which leaves us with the clear winner of the interactive test.
Claude Opus 4.8 won this, hands down. It was the safest choice for smooth controls, the gameplay was stable, and the physics actually felt right to the human hand.
This points to a fascinating divergence in how these models are being trained and optimized.
Here's where it gets really interesting. GPT is like a highly technical, uncompromising architect.
Okay.
It builds a mathematically perfect, structurally sound house where all the angles are exactly 90 degrees. But Claude is the interior designer. It actually makes the house comfortable to live in.
That is a great way to visualize it.
Uh-huh.
Claude focuses heavily on human-computer interaction.
But I don't understand how a massive matrix of numbers even knows what smooth gameplay feels like. It doesn't have hands.
True.
It doesn't play games. Why does Claude excel specifically at the interactive parts?
It comes down to the underlying training mechanisms. Claude appears to be heavily tuned via reinforcement learning from human feedback. Exactly. And specifically tailored toward user experience. Its training data likely prioritizes front-end stability, React components, and user interface frameworks. It learned the statistical patterns of what humans rate as a good interface.
Claude prioritizes how the code actually feels to a human.
Pete. And that makes it an exceptional partner for front-end developers.
But creating from scratch on a blank canvas is only one type of skill. Navigating someone else's messy, undocumented logic requires an entirely different type of intelligence.
Reading code is notoriously much harder than writing it. It is the most agonizing part of software engineering.
We are looking at Pawa Hurin's test next. This was a brutal 21 bug hunt. He planted 21 highly complex hidden bugs inside a real existing code base.
This is the perfect real-world scenario. You aren't building a shiny new toy. You're acting as a mechanic trying to fix a broken machine without a manual.
They tested the model's ability to find these bugs, specifically measuring the impact of giving them maximum reasoning time. Claude Opus 4.8 was a solid code reviewer. When given more time to think, it actually improved significantly.
It used that extra compute time to trace variables carefully through different files.
But GLM-5.2 stayed completely flat. Turning on higher reasoning did not help it catch a single extra bug. It just hit an immediate plateau.
This exposes a critical architectural weakness in current open-weight models.
GPT-5.5, however, absolutely dominated this bug hunt. Max reasoning made a massive difference.
Yeah.
It systematically hunted down the errors, making it the clear, undisputed winner for deep debugging.
This highlights a deep philosophical difference between generating code and debugging code.
Yeah.
When you generate new code, you control all the variables. You are the master of the logic you are creating.
But debugging isn't creation, it is forensic accounting.
Yes.
You have to track down someone else's embezzlement of memory. You have to extract intent from someone else's chaos.
Exactly, because you are looking for the logic that is missing, or the logic that silently contradicts itself. GPT clearly possesses a superior analytical engine for tracing those long, convoluted threads of state and memory.
Why did the open model hit a wall when given more time to think? Why couldn't GLM use that extra time to trace the variables like Claude did?
It comes down to reasoning ceilings. Giving a model more time only helps if it has the architectural depth to form new analytical pathways.
Right.
If the model's core reasoning engine is shallow, extra time just means it repeats the exact same flawed analysis in a longer loop. It doesn't magically develop deeper comprehension.
GLM hits a strict reasoning limit no matter the time given.
It is a fundamental limitation that open source researchers are still desperately trying to solve.
So what does this all mean for you, the developer, sitting at your keyboard today? Let's synthesize the ultimate takeaway from all these conflicting metrics and tests.
The biggest realization is that there is no universal winner. The idea of one model to rule them all is dead. You have to match the specific model to your specific workflow.
If you are building interactive UIs, if you are rapid prototyping games or throwing together visual demos, you should be using Claude Opus 4.8.
Definitely.
It intrinsically understands human feel, smooth interaction, and front-end stability.
It is the clear, unrivaled choice for any user-facing application.
But if you are doing deep logic work, if you are reading heavy legacy code bases, migrating databases, or doing complex forensic bug hunting, you need to use GPT-5.5. Its analytical reasoning and ability to trace variables across files is currently unmatched.
It acts as your senior back-end engineer and your most pedantic code reviewer.
And what about GLM-5.2? It is not useless. You should use it as a powerful API testing ground.
Right.
If you have high-volume, low-complexity tasks, it is a great tool. Just make sure you carefully monitor your token counts so you don't fall into the cheap token trap.
It is pushing the boundaries of what open models can achieve, even if it hasn't completely conquered the reasoning ceilings yet.
I want to leave you with a final thought to mull over. We have seen that these models can build entire physics engines from a single prompt.
Yeah.
We have seen them hunt down 21 complex bugs simultaneously across dozens of files. But all of this relies on humans grading the outcome. What happens when these systems become so advanced that humans can no longer comprehend the code they write?
That is a scary thought.
What happens when the AI starts writing the benchmarks to test itself?
That is the singularity of testing. When they start grading their own homework, our entire definition of a benchmark fundamentally changes. We won't even know what they're optimizing for anymore.
It is a wild frontier. We encourage you to run your own side-by-side cage match this week.
Absolutely do it.
Take your most frustrating, tangled current project, feed it to all three models, and see what happens. You might be deeply surprised by who actually fixes the mess and who just hallucinates a bigger one. We will see you next time. Out Hero Music.